those of you in Australia and Asia. Welcome to Session 8 of the ESIG 2021 Meteorology and Market Design for Grid Services Workshop on the topic of forecasting, reserve requirements, and system operations. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As I think you know by now, our workshop sessions are all being held online and are open to everyone. And I do want to let you know that we're planning our first major in-person event since the COVID outbreak last year with the Fall Technical Workshop in Austin, Texas, during the week of October 25th. Please mark your calendars and look for additional information in the near future. This workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoivasan of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who really make ESIG what it is, and we encourage you to become involved if you're not already. You can find us on the web at esig.energy, send an email to info@esig.energy to get our monthly newsletter, and follow our activities on LinkedIn, Facebook, and Twitter. ESIG also serves a leadership role in the Global Power System Transformation Consortium, often called GPST, whose mission is to bring together key actors from around the world to catalyze a rapid, clean energy transition at unprecedented scope and scale. ESIG leads one of the 5 pillars that deals with the research agenda for the system operators. More information on GPST can be found at globalpst.org. Regarding logistics for today, I would ask you to note that Session 8 will be an hour and a half long. We had a lot of feedback that our 1-hour workshop sessions were too rushed, so we've moved to some longer formats for this workshop. We'll have 4 individual presentations during the first hour, followed by approximately 25 minutes of discussion and Q&A after the last speaker. As we're doing with all of our webinars now, we'll be using the Slido platform for managing the Q&A. You should go to slido.com on your device and enter ESIG24 as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also at the bottom of the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we'll address them at the end. We'll follow up with any written answers to any questions we don't get to during the Q&A. Recognizing the limitations of a webinar with more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG24 as the event code. Today's session is titled Forecasting, Reserve Requirements, and System Operations. This is a topic affecting everyone who is operating a power system, and one which goes back to the roots of this particular workshop series. We have a fine lineup of practitioners and participants from across the spectrum today who will explore different aspects of this topic, and I'm looking forward to a great session and discussion. The session will be chaired by Aidan Tuohy of EPRI. Aidan is a well-known figure in the system planning and operations space, now serving as a program manager at EPRI, after graduating from UC Dublin with a PhD in EE in 2010. Aidan is a co-chair of our System Operations and Market Design Working Group at ESIG, and head of the Flexibility Task Force. He's a good friend, a regular contributor to ESIG activities, and is well known to many of you. He brings a lot of good experience and insight, and we're very happy to have him here with us today. Aidan, we appreciate your participation, and I'll now turn it over to you.
Thanks, Charlie. Appreciate the introduction and the opportunity to chair today's session. So we've got a very interesting session today lined up. We're going to get straight to it. As Charlie mentioned, we've got about an hour of presentation. Tassos is going to take a little bit of a shorter presentation and give an update on the DOE solar forecasting work, and then Nitika, Damian, and Rhett will give presentations that are a little bit longer, get into some of the details around the topic. So with that, I'm going to hand it off to Tassos. Many of you know Tassos from previous ESIG workshops. He's a technology manager with DOE's Solar Energy Technologies Office. He spent 4.5 years at the Systems Integration Team, where he supported the solar forecasting activities, including the funding opportunities and workshops. And then last October, he joined the photovoltaics team to support the modeling and performance analysis activities, including AI-based solutions. Prior to joining DOE, he spent 15 years in the semiconductor equipment and solar industry. So Tassos, if you want to take a few minutes and tell us where DOE is.
Sure. Thanks, Aidan. Welcome, everybody. I'm very happy to be given the opportunity by ESIC to give you a short update on what we're doing at CETO and DOE when it comes to forecasting related activities. So hopefully I'll be able to change my slides here, and we should see the second one. So this is the list of the major things that are going on right now, right? So the solar forecasting 2 projects that were awarded about 3 years ago, almost, to the day, are wrapping up by the end of this calendar year. The major activity that's left on these, 8 R&D projects is the cross-evaluation of the model performance, right? So 7 of these projects were tasked with developing better models for solar forecasting. So 4 of them were focused on solar irradiance, and 3 of them focused on forecasting of solar power and its integration with the operations in energy management systems. So we have asked all the teams to essentially provide forecasts in 10 locations in the continental US, representing essentially the major climate regions in the country. 4 teams will be providing day-ahead hindcasts for the entire 2018 calendar year. That's obviously the 4 teams that were working on solar irradiance R&D. And 3 teams will be providing day-ahead power forecasts, irradiance forecasts for 3 months between August and October 2021. These are the 3 teams that we're working on the power forecasting R&D. At the same time, the Arbiter, which is the 8th team that was awarded in solar forecasting 2, and was tasked with developing this open platform for evaluation of forecasting models, is at the stage of exploring operational trials with several end users. I'm not authorized to give you more information there, but we're very excited by the traction the platform has achieved in the community. The solar forecasting workshop, an activity that we do every 2 or 3 years, and this year was completed in May 21, early May of just a few weeks ago. I'll give you a few more details about that in the next couple of slides. And finally, we have 3 machine learning projects around net load forecasting that essentially came off of our major funding opportunity in last year. They're just starting their work pretty much as we speak. We have a couple of them that are led by national labs, and they've started a little earlier than everyone else. But again, this summer, we have all 3 of them essentially started work on their tasks. So a few words about the workshop that took place on May 5th and 6th. We had keynotes from respected members of the community, from the R&D to the operations to the consultancy contingency. We had a great slew of panel presentations and a discussion with 5 major ISOs from one coast to the other. We had presentations from all awardees from the Solar Forecasting 2 program, and we had a live demonstration of the Arbiter for about, for the 80 people that were able to join our workshop, which was a record, at least as far as I have been with DOE. Last but definitely not least, we had 2 breakout sessions, one on each day, to have informal discussions with the participants about the trends they see in solar forecasting, about the priorities they think that DOE should look at. And for that, I have a brief update for you guys. This will all be presented in our website in a few days, but this is a preview. So we took notes during those discussions, and then we essentially distill them in those four major areas, right? So when it comes to forecasting models, everyone said, please support the subgrid scale cloud research. Make sure that sort of forecasting R&D on all time scales is supported. And there was, again, voices about better awareness of the operational models that are put out by NWS and NOAA to support integration of the research models that DOE CETO is funding. The solar-related use cases, again, strong support for the forecasting of behind-the-meter solar, as well as on the focus on the impact of the extreme events on solar plants. On the data and sensor side, again, people mentioned the need for higher quality and also the availability of ancillary data. And they, again, mentioned the importance of observability of behind the meter being still a key issue in achieving better forecasting results. Finally, there was, again, a request to assist with access to data, including behind the meter data. And technology transfer, an area where we are keenly interested in. I think we know that ensuring engagement between the R&D vendor and end users gives the best results. We realize that the solar forecast arbiter needs wider outreach, despite the great effort that the team has made over the past few years. We still need to get more people aware of it. And finally, demonstration to operators is a key aspect for adoption of these R&D models. And I think I'll stop here and take any questions, either now or later in the schedule.
Thanks, Tassos. Appreciate the quick update. And if folks do have questions, do put them into the slider.com, the ESIC24, the website there, and we can come to them at the panel discussion here at the end. So appreciate that, Tassos. Thank you for the update. The next presenter is Nitika Mago from ERCOT. She received a BSEW degree from University of Mumbai and a MSW from UT Austin. Has been working at ERCOT since July 2007, where she's currently the manager for Balancing Operations Planning Department. Her areas of focus are power system grid operations, renewable integration, ancillary services, data analytics and modeling, and she's a registered professional engineer since 2011. So Nitika is going to talk about some of the ERCOT experiences here. I'll turn it off to you, Nitika.
Hey, thank you very much, Aidan, for this, and hello, everyone. I'll take a few minutes to share with you the forecasting practices for wind and solar resources, catch you up on some history of the work that we've done in the past, where we are today, and what changes we are looking to bring in for the future here in the near term. Here we go. So before I actually get into the meat of my discussion, just introducing ERCOT to those who are not very aware of ERCOT through our record perspective. Our peak demand record was set in summer 2019, August 12th, 74,820 megawatts. Recently, in the week of Feb 14th, we hit a winter peak demand record, which came very close to our summer peak number, 69,812 megawatts. We are generally a summer peaking region. From a wind perspective at this point, still focusing on wind. Our peak wind generation was from earlier this year, January 14th, and the peak record was around 22,893 megawatts. Peak penetration record occurred on March 22nd, 2021. On this day, during that time, that's quoted, about 66% of our load was being served by wind, and that megawatt quantity was around 31,574 megawatts. So, incidentally, at this time, this particular hour, we also made I reached the lowest system inertia that we have seen here in the recent past. The system inertia was 109 gigawatt seconds. That is by far the lowest inertia level that we have operated our grid on. So here's a look into the amount of wind and solar additions that we've made by the year. Now, the quantities that you're seeing here are utility scale transmission connected wind and solar resources. Of course, our solar resources have started coming into our grid more recently, and we have an outlook which shows that we will, today we have about 4,395 megawatts of solar. We will add, we are projecting to add another 12,000 more megawatts by end of 2023 for solar resources. Wind, we today have about 25,642 megawatts of wind that is installed, and we are projecting to add another 5,700 by end of 2023. So the outcomes in the future are certainly uncertain, but that's the outlook into our pipe. There is still a lot more wind to come. There is still a lot more solar to add into our grid. So overall, our installed total wind plus solar capacity is just shy of 30,000 megawatts right now. That's just a little bit. Next slide. Here we go. Okay, so now let's start talking about forecasts. So ERCOT implemented a centralized forecast for wind and solar resources. Wind, we implemented it in 2009. For solar, we implemented it in 2016. In 2017, we contracted a second provider to provide wind forecasting services. So all in all, we have two providers who provide forecasts for wind, and we have one provider that provides forecasts for solar resources. Now, in terms of models that we receive, ERCOT receives an hourly forecast for each wind and solar resource. We receive an extreme event forecast, again, right now only for our wind resources. Both this hourly forecast and the extreme event forecast are at an hourly resolution for the next rolling 168 hours. And of course, they are updated at an hourly pace. The second set of models that we receive are intra-hour forecast. We receive an intra-hour forecast both for wind and solar at system level. So this is essentially giving us a 5-minute resolution forecast for the next 2 hours, and it is updated every 5 minutes. As y'all are probably very familiar, for those of you who are into the forecasting world, the primary inputs into this forecast are, of course, site locations, geolocation, wind speed, temperature, operational limits, telemetered site-specific data, scheduled outages and derates, and generic power curves, and weather variables. Now, if you look at on this graph, in this slide, I also included just an annual forecast performance on an annual basis, and you'll notice we've made steady improvements both for the wind forecast and the solar forecast. Today, our 2020 average forecast error for wind in the day ahead was around 4.28%. In the hour ahead was around 2.36%. For solar, those numbers are a bit higher. Our day ahead yearly average error is around 5.84. The hour ahead is around 4.8%. Now, one other graphic that I wanted to share with you is since about 2018, we have put into place a pay for performance model for our wind forecast vendors. And through this model, what we are doing is we are incentivizing our vendors to improve forecast performance during hours that are of importance to operational reliability. So hours where there is a large down ramp, hours where that we call quote unquote as high risk hours. So hours where typically the high risk category would be hours where we typically see a risk of a net load up ramp, or peak load hours. So these would be the hours where we want to incentivize our vendors to perform to improve their forecast performance. And in front of you is a graphic that shows you how the MAE, the mean absolute error of forecast in those specific hours have been. In purple, we are tracking the large down ramp hours. In orange, I'm tracking all of the high risk hours. And generally, I mean, you'll start seeing the trend for these high risk hours is fairly tight. The error magnitude over time is fairly tight. The error magnitude on the large down ramp has overall just trended lower than where it started. Probably picked up a little more here in the recent past, but we've also added a lot more installed capacity between when we started and where we are today. So this pay for performance model has certainly helped us put highlights on hours that are critical to our operations and focus on and incentivize improvements in forecast in those hours. So now continuing that same theme of what other noteworthy forecast improvements we've made. And this slide sort of lists quite a bit, and I'll probably just highlight a few that had quite a bit of impact. So in 2015, following some experience we had with cold weather operations of wind resources, we obtained the capability to override manually the wind forecast that we were receiving. So essentially the idea was times when the meteorological conditions weren't being captured appropriately by the forecasting process, our control room would have the ability to influence the forecast that we were receiving. And this is important because the forecast that we receive gets used in all of our look-ahead studies, so reliability unit commitment, outage coordination, next day studies, all use the most recent forecast we receive. So we want to make sure that those forecasts are appropriately capturing the conditions that the grid will be experiencing. In 2017, we also added a new desk in our control room called the Reliability Risk Desk. And really the background here was with the amount of wind and solar resources that we were adding, the type of variability the type of risk assessments the control room was having to do was growing, and we felt there was a need to where we needed a dedicated desk in the control room to run those what-if assessments, to run those risk assessments and communicate with the traditional desks on actions they may need to take around ensuring the forecast that they are selecting is appropriate for conditions that are coming on ensuring that the units that are operating are following our performance requirements the way we want, and so on. Like I said, a couple other points. In 2018, we integrated our intra-hour wind forecast into our security-constrained economic dispatch process. Recently, we've done an update to include intra-hour solar forecast into our same dispatch process. And I've got a slide that talks a little bit more about what we've done, so I can touch upon that in a little bit. Moving on to the next slide. So we had in around 2017-18 time frame created a dashboard in our energy management system that tracks the latest and displays the latest hourly forecast and the intra-hour forecast on a system level basis to our control room. And the control room, so in front of you, the picture that you're seeing here is showing you the quote unquote the hourly forecast. And what you're seeing in front of you are really, there are 6 different models that are available to the control room today, 3 from each vendor. So we have 2 vendors. So the STWPF, which is the 50th percentile probability of exceedance model. The extreme weather has 2 versions of it. So they've got extreme weather 1 and extreme weather 2. So and the control room has the ability to go select which model will be active. Now so through this we influence, or we make sure that the forecast that is selected represents the conditions that will be coming. Philosophically, the way this display was set up, it was set up to replicate the existing displays we had for load forecast. So load forecast is also something that is inherently built into our EMS, and the control room has the ability to toggle between models based off of the conditions that they expect to be the most representative of the grid conditions. And this display was very similar in its usage to that particular tool. Let's see. While we are talking about the extreme weather forecast, I also thought it might be useful for this audience. Here's an example of how our icing forecast behaved, or the extreme weather forecast behaved during the extreme temperatures we experienced in the week of Feb 14th. We experienced about at the height about 7,500 megawatts of outages on our renewable fleet. And what you'll notice is that as the shades on the darkest shade on this darkest shade line on this graphic represents the very first forecast that we received for Feb 14, Feb 15, Feb 16, and then as the shades decrease, you're seeing a more recent forecast that was generated 12 hours later. And what you'll notice is that the quantity of the magnitude of impact that our forecast was predicting started adapting to conditions on the ground. So as the conditions on ground worsened, our wind resources started submitting outage data in our outage scheduler, and the forecast that we were receiving started showing us only what was the remaining forecasted impact, essentially. So through this, we were able to continue to maintain awareness of our line of sight on what we could expect the supply from our wind resources to be during that extreme weather period. So I'll now talk a little bit about this very recent change that we implemented, which was about integrating the intra-hour solar forecast into our systems. And primarily, we are using it to supplement our dispatch calculations. So let's see. We have a calculation in our energy management system in our EMS, which sets the total target dispatch that SCED will use to dispatch resources. Our SCED assumes that our wind and solar resources output will persist, so it technically does not dispatch them. It only dispatches non-wind, non-solar resources. And what we did is we included, we updated the target that we were feeding to our SCED engine to include include forecasted solar ramp. The idea being at times when solar was expected to ramp down, we would send a higher target to SCED so that it could dispatch non-IRR resources in response to the anticipated decrease in wind. So it would pre-position our thermal resources, loosely put, in response to the change in the solar output. In front of you is a graphic that shows you a performance metric of that of our calculations. In blue is the error if we assumed. Actually, hold on a minute. In blue is the error. The labels here are toggled, so I apologize. In blue is the error if we were to assume persistence as the only mechanism to feed our SCED dispatch. In gray is if we were to use the forecast, and generally using the forecast, the amount of error in our dispatch reduces. The MAE becomes lower. And you see that in the table up there. The MAE, the monthly MAE for if we use just the forecast is 60 megawatts, whereas if we use persistence ramp, it's 85. And if we only focus on times when there is a ramp in our solar fleet, you see the magnitude of error goes up, but the forecast still continues to be better than persistence. So this was a very fairly recent change that we brought into our tools, and we are still monitoring this as time moves on. Okay. Lastly, here's probably one more set of changes which talk about where we are headed in the future. So ERCOT is planning to develop a web-based forecast presentation platform that is envisioned to be used to display, select, monitor all types of forecasts, so load, wind, solar. We are looking to migrate to this web-based display as our source for those forecasts. The primary drivers for envisioning this change is, A, there is a growing functionality need. So, for example, we want to add more models, make more models available to the control room for the forecast that they are looking at. And I mean, example could be today there's a 50% probability of exceedance, but we also get a higher probability of exceedance, 80% probability of exceedance, which is a more conservative forecast. We want to add a blended forecast, which blends, probably blends the forecast from the various models that we have. We want to incorporate some way of another forecast, which probably represents the worst forecast for the weather pattern that we are experiencing. So there's a combination of things we want. Let's see. Next, also, our ERCOT market has passed some rules which says, hey, when ERCOT control room ends up making forecast selections that don't, that are more extreme, that are more outliers compared to the average that we are seeing for those hours, they want to be able to understand why we are doing what we are doing. And the next, what we realized is as our needs were evolving, our current technology, our current platform that of the EMS that is was fundamentally not designed to track forecast-like data and associated functionality needs. And so we've already, what we've built for wind and solar is considered custom code. And ERCOT has adopted this policy to reduce the number of custom codes we have in the EMS. And for those of you who've been involved in EMS upgrades, customs end up affecting the amount of time it takes to migrate from your current version to the next version. So all of this is factored into to developing this concept of a web-based forecast presentation platform. And currently what we are thinking is, of course, we'll be, as far as scope of work goes, we'll migrate the existing functionalities that we already have. We'll update after we've done migrating, we'll take on the job of updating, capturing the functionality needs, which is adding more models. We also want to include online forecast performance tracking in this tool. So that's what we are envisioning. We are targeting to complete this implementation by summer next year.
Nitika, if you could finish up in the next minute or two.
I can do so. I don't think I have much left. Well, okay. So I'll skip over this. We've talked about this already. So the last piece that I wanted to share with you, and I can probably make this point better in terms of this tool that we have here. We've also been working on putting together more operational tools into our control room. And this particular graphic that you have is a tool called a capacity availability tool. Through this, we help the control room run some what-if assessments. So the traditional problem your control room is looking at is, do I have sufficient capacity to serve the forecasted demand? Through this tool, the control room is able to apply uncertainties on the renewable fleet, uncertainties on the load. So what happens if what happens if I'm under forecasting my load? Do I still have sufficient capacity to serve load? What happens if I am over forecasting wind generation? Do I still have sufficient capacity to serve load, or do I need to take certain actions? So through this tool, we help the control room run those type of assessments. And essentially make decisions on whether they need to deploy reserves considering if there are net load forecast errors that they see coming down the pipe that they don't think are fully captured by the by all of the processes leading into the real time. So this is my last slide. I'm happy to take questions when we get to that portion of the discussion.
Thanks, Nitika. And I do see quite a few questions coming in for you on the Slater.com page. So if folks have questions or comments for Nitika, please put them in there, or for the rest of the panel. With that, we'll move to the next panelist. So Damien Flynn, who's an associate professor in power system operation and control at University College Dublin, Ireland. He's 25 years experience around power system dynamics, grid integration of renewables, power generation control. He's widely published, over 250 papers and 3 books and studies. He's been involved in quite a few European projects recently, as well as Irish government projects, and is the national task participant in the IEA Task 25 expert group, as well as International Federation of Automatic Control Technical Committee. So Damien's going to talk about some of the recent experiences in Ireland, and Damien, I'll hand it off to you.
Hello, Aidan. Thank you for the introduction and welcome to Dublin. So as Aidan said, I'm going to talk a little bit about the Irish power system, a bit about the present day power system and the future plans for the system. So if you're not familiar with the Ireland power system, this is just a slide with a few summary facts. So peak demand, just under 7 gigawatts. It has a sort of an all-island market. There's HVDC interconnection with Great Britain. Wind capacity about 5.5 gigawatts. Peak wind is about 4.5 gigawatts. We have a little solar as well. And annual wind share last year was about 36%. Maximum wind penetration in Northern Ireland, you can see it was about 150%. In the Republic of Ireland, it was just under 100%. And across the island, the maximum wind share is about 95%. And then finally in this slide, I mentioned the SNSP limit. So SNSP stands for System Non-Synchronous Penetration Limit, which is the amount of non-synchronous wind and PV that you can allow on the system. And currently that limit is 70%, although the record is at 71.8%. So if I just quickly summarize a few major operational rules for the system, which will give an introduction to later sections. So there are rules on terms of minimum number of units on the system, so that there needs to be at least 8 large generators on the system. They need to be distributed around the system. I mentioned SNSP, so at the minute that limit is at 70%. There's currently a trial underway to raise that limit to 75%. And then there are also various, I suppose, dynamic limits, rate of change of frequency. Currently, the limit is 0.5 hertz per second. There are trials underway at 1 hertz per second. And there's also an inertial limit of 23,000 megawatt seconds. So just to illustrate SNSP, this is a graphic from a couple of weeks in February of this year. And you can see that the SNSP is sort of spending a lot of its time bouncing around at 70%. And as I say, the current limit is 70%. There's trials operating at 75%. So what we have in Ireland is a system that is operating at its limit in terms of system stability at certain times. And that does mean that there is curtailment or constraints on the system. If I can just introduce some sort of nomenclature for Ireland. Ireland uses the collective term of dispatch down, and then it splits that up into constraints, which are marked in blue here. So constraints tend to be local network constraints, or let's say voltage stability constraints, and curtailment tends to be system-wide constraints or system-wide issues. For example, SNSP or minimum number of generators online. So last year, you can see that the levels of wind dispatch down were quite high, roughly 10 to 12%. partly because it was a windy year last year, but also because of COVID, the demand was depressed last year. So those figures are much higher than they would normally be. As I say, we also have some solar. The solar is concentrated in Northern Ireland. It's not because it's sunnier in Northern Ireland, it's just because there are incentives in Northern Ireland which don't exist in the Republic of Ireland. But again, you can see that there is curtailment taking place. If I speak briefly about wind forecasting, so in Ireland there are 2 vendors, and they provide a long-term forecast and a short-term forecast. So the long-term forecast is looking 5 days ahead, 50-minute resolution, and that is updated every 6 hours. And then there's also a short-term forecast, which is looking 12 hours ahead, and that is updated every 15 minutes. So in the top here, what you're looking at is, I suppose, the purple line, which is the actual wind, and the red line, which is some sort of blended forecast. So the system operators see both forecasts, and then they decide which ones they want to use. What they might also do as well is that perhaps at night time, they will tend to use the high forecast because they're concerned about minimum generation levels. And during the daytime or early evening hours, they would tend to use the lower forecast because they're concerned about having sufficient thermal capacity online to meet the demand. And then the lower forecast, or the lower figure there, is showing the forecast in green, the actual wind in blue, and then you have confidence limits sort of expanding out over time. And those are particularly important when the operator is thinking about ramping needs for the system and perhaps bringing on generation to cope with future uncertainties. So there are also a number of system services on the system. So traditionally, there would have been 7 system services. In the last couple of years, because of the levels of wind on the system, that number has increased to 14. So you can see there are 3 additional ramping products. There's also a synchronous inertial response product, which is designed to, yes, give you synchronous inertia, but also to reduce min-gen levels on the system. And then also a number of fast acting products, which I'll talk a little bit about later. These system services are arranged either through tariffs or contracts. So there are set prices, and then there are a number of scalers which encourage people to improve their performance. So if you can provide faster than default response, you get a larger payment. If you can provide a dynamic response as opposed to a stepped response, again, you get a larger payment. If you're able to supply a number of products in sequence, so from a fast frequency time frame through a primary, through a secondary, through a tertiary time frame, again, you get increased payments. So it's about encouraging flexibility to the system and going beyond the standard definitions of the products. So that was sort of a quick overview of the present day. So if I now sort of look towards the future. So in 2019, the Irish government released its climate action plan. And that climate action plan targeted, amongst a number of things, 70% renewables by 2030. And you can see it was expanding the amount of onshore and offshore wind, adding more solar to the system, and also looking at electrifying heat and transport. Since 2019, there has been a change of government in Ireland, and the new government, the Minister for Energy is from the Green Party, so that has very much encouraged the Irish government's motivation to, I suppose, do more in terms of climate action. So earlier this year, there was a climate bill released, which targeted 51% emissions reduction. And that emissions reduction, if you work it out, is actually more ambitious than the various renewables targets and the onshore wind and grid scale solar. So it's expected within the next couple of weeks that these existing targets are going to be further raised. So we have high ambition as it is, but that ambition is going to be increased. That would be the expectation. So what does that mean for the future? So this is sort of a brief schematic of the present day system. So on the left-hand side, we have the demand. On the right-hand side, we have the generation. If I look forward to 2030, the demand is increased because we're electrifying a lot of sectors in terms of heat and transport. Most noticeably, there's expected to be a very large growth in data centers. So it's expected that in 2030, perhaps 30% of the load in Ireland will actually be coming from data centers, and that will be concentrated in Dublin. There will also be very large growth in wind, both onshore and offshore. And what I haven't shown in this figure is there will also be growth in solar PV as well. So it will be a very, very changed system. So if I just look at some of the implications of this, so here we have a cumulative distribution plot sort of showing in the thick blue line the probability of certain levels of wind and solar on the system. And if we look at the green dotted lines, which is sort of 75% system non-synchronous penetration, you can see that that equates to roughly 50% of the time. So in other words, for roughly half of the time, the amount of available wind and solar will exceed the existing stability limit. There is a target for 2030 of a 95% SNSP target. And you can see, even with that, the dotted blue lines is getting the share up to 60% of the time. So it implies that for roughly 40% of the time, the wind and PV will exceed the demand. Of course, it also is the possibility that wind and PV can be very low. And I'll come on to that point a bit later on. So it just illustrates the challenge that at certain times there's going to be a large excess of wind and PV on the system. At other times it's going to be a shortage. And Ireland is an island system, so it has limited export opportunities. So as part of a European project, EU Sysflex, which is led by ERCOT, one of the things that was done across the European system was to look at the scarcities in terms of stability challenges, and that was done for continental Europe, Ireland and Northern Ireland and the Nordic system. And if we focus on the Ireland and Northern Ireland system, you can see, perhaps not surprisingly, given Ireland's ambition and given that it's a synchronously isolated system, that there are a lot of red issues. There are a lot of stability issues that need to be resolved. So just to illustrate some of those aspects, here is a plot on the left-hand side. It's the frequency nadir, so you're losing your largest in-feed. On the right-hand side, you're losing your largest outfeed. So it might be that Ireland is exporting power to Great Britain or France. And you can see, I suppose the good news is that it is possible to maintain the frequency within reasonable limits. Yes, it falls beneath 49 hertz, but not too far for extreme events. And similarly, if we lose a large outfeed, the frequency can be maintained up to 50.7 hertz. So it's a challenging situation, but it's manageable. If you then look at individual traces, you can actually see that there is quite a lot of variation. The first thing is that because you have a very high wind and solar PV system, things happen very quickly, and you can have cases of low frequency transients, but you can also have high frequency transients depending on how you set up your static reserve for the system. As you remove more conventional generation from the system, then steady state reactor power becomes a challenge, and hence there's a need for steady state reactor power system services. Similarly, your network can become overloaded. So at the moment, there isn't any congestion related system services, but there are thoughts that perhaps in the future, there might be system services that encourage congestion relief measures. And of course, if you look at fault conditions as well, this is looking at faults in 2 different locations, A and B, 2 different time steps. And if we focus on the green curve, you can see that there is a lot of oscillatory behavior, which again is promoting the idea of a system service related to dynamic reactive response. So I suppose those stability issues are reasonably familiar. If I mention one that is perhaps not quite so familiar, the idea of a voltage dip induced frequency dip. So on the top curve, the voltage trace, we're looking at a voltage dip that has occurred somewhere in the network. And in the lower figure in red, what we're showing is, I suppose, the typical response of a conventional generator. So that once the fault clears, the power output quickly recovers to its nominal level. For a wind turbine, it may take some time for the wind turbine to recover to its full output. And so there is a power imbalance briefly, hence the shaded or hashed blue area. So the concern would be that if you have a fault in, let's say, the red location on the map, and you've got a lot of wind turbines or wind farms nearby, then they could all see a large voltage dip, and then they could all see a drop in power for a short period of time. And this is just an illustration of the problem. And if you look at the lower figure, you can see that the power imbalance goes down to a level of sort of 3,000 megawatts. And to put that into context, if you remember back to my earlier slide, I was talking about the Irish system having a peak demand of 6 or 7 gigawatts. So losing 3 gigawatts, even if it is temporarily, is an interesting problem to solve. So the solution has been to modify or propose modifications for fault write-through characteristics. So originally, the recovery time was set at 1 second. That was reduced to half a second. And a system service has also been introduced called the post-fault active power recovery service, which further encourages participants to provide a response within 250 milliseconds or to recover within 250 milliseconds. If I can also talk a little bit briefly about 100% SNSP. So yes, Ireland is looking at 95% SNSP by the end of the decade, but that's not too far away from 100% SNSP. So as part of another European project known as the Migrate project, studies suggested that perhaps a third of converters, whether they be wind or PV, should be grid forming. And it would be beneficial if that grid forming capability was distributed around the system. One thing that is being looked at is just to see what happens if those grid forming converters are using different control strategies. So there's a wide range of options available. I'm just mentioning a couple here. But this is just an example where you're seeing a 3-phase fault is being applied near Dublin, and some of the converters are using traditional droop control. Some of them are using oscillator control. And what you can see is that the system remains stable. So that is good news in that we can get away with using a mix of different controllers, and the system is able to operate in a robust manner. So the final thing I want to talk about is, again, going back to forecasting, but I'm using forecasting here in perhaps a slightly different timescale to the other presenters. So I'm looking at forecasting towards the end of the century. And what I'm thinking about here from a system adequacy point of view is, as we add more wind and solar to the system, is there the possibility that there will be periods of insufficient generation to meet the demand? And this is sort of looking at 2080 to 2100, so the end of the century compared to the end of the previous century, and comparing winter against summer. And if you look at the winter timescale, what we have in the vertical lines is a number of different forecasting tools. And the sort of the gray box is sort of the mean of those forecasts. And what you tend to see is that in winter time, it will tend to be windier. and in the summertime, it will tend to be less windy. So the winter time, that's good news for Ireland because it tends to have a winter peak. In the summertime, it will be less windy, but the contrast is that there should be solar PV on the system, which will help under those situations. And as I say, the question of interest is looking at periods of extended low power. So my definition here is a period of 1 day or longer whenever the power levels are less than 10%. And what you would like to see is that you have fewer events and those events are shorter. So essentially you're in the bottom left quadrant. And what you would like to avoid is that you've got more events and that they are longer in duration. So the good news is if you look at the winter columns is that there isn't expected to be too much change. The bad news is that during the summertime, it is likely that you will get more extended events and they will be longer in duration. But there is some further work to do here in terms of adding solar into the system, which will hopefully give a better story or a more positive story. So if I just end up with some final questions that I suppose are of interest to all systems. One, Ireland is looking at how it can achieve cost-effective operation with increasing renewables and getting closer and closer to a system that is just wind and PV effectively for significant periods of time. A challenge for many systems is how can you do this without building new transmission lines? And how can you maintain system adequacy if you're moving to variable generation? And I maybe just leave with the final question is that a question that many systems are seeing is that all the easy stuff has been done. And perhaps we need to change our focus into focusing on CO2 reduction and doing that as our objective rather than least cost solutions, which may mean that we look at different solutions rather than focusing on pure economics.
Thanks, Damien. We appreciate the presentation, very interesting, and hopefully a lot of good questions coming out of that. If folks do have questions, do add them to the Slido page. So the next speaker is Rhett Trease, or the final speaker is Rhett Trease from Duke Energy. Rhett's a lead engineer. He's worked in real-time operations and our unit commitment in all of Duke Energy service territories. He's a former load and solar forecaster and was a lead engineer in their fuels and system optimization before moving to his current role in the integrated system operations and planning group. So Rhett's going to talk a little bit about how Duke are thinking about reserves and forecasting.
Excellent. Thank you, Aidan. Thank you for having me today. For a little background on Duke Energy, you know, I know we have a kind of international audience here, so we serve residential load and regulated load in 6 states. We're the largest utility in North and South Carolina, largest in Indiana, second largest in Florida. You'll hear me talk a little bit about DEC and DEP. DEC is generally the western side of the Carolinas and the legacy Duke BA, for those that are familiar. And then the eastern side of the Carolinas is, we call it DEP. It's the legacy Progress Load. It's generally the eastern half of the state and a little bit of the mountains here. Serve 7.8 million customers and a little over 5 gigawatts of regulated generation. We also have our commercial side of the company with a little over 2 gigawatts of renewable generation. Let's see. And some of the challenges we're facing here sound kind of familiar to everybody else. North Carolina is the largest state in the country for PERPA solar penetration. We have a lot of solar in DP already, and it's growing at a very steady and predictive rate. We have a lot of DC. It's starting to pick up in the Carolinas, and certainly in Florida, it's picking up at a very fast pace, both rooftop and utility scale solar. You know, one of the challenges we face in the southeastern portion of our territories is we tend to be winter peaking, which is a little backwards, but it does get cold in the south, and we have a lot of heat pumps and a lot of resistive and electric heating. So we have a lot of solar. It's not very windy towards the southeast U.S. There's not a lot of wind generation, but a lot of sun. So a lot of solar. And we'll tend to peak, you know, in the morning when it's dark out, and you know, then solar will pop up, and these ramps are starting to get fairly severe. Then they'll go away, and we'll get our typical duck curve. In the Carolinas, we also have 11 nuclear units, so we don't always have a lot of, you know, load to play with and generation to move around in the afternoon with the, you know, non-dispatchable nuclear units. We're starting to see a lot of backflow issues, you know, more local issues as was shared in the ERCOT presentation. And then, you know, just generally, we're starting to see a lot, you know, more demand from our customer needs. We're seeing a lot of, you know, EVs and grid storage or fleet charging pop up. A lot more rooftop solar. You know, can be a few hundred customers a month. EVs and, you know, grid storage. Lots of new things happening, and I don't think that's news to anybody on the call. Let's see. So we'll move on to the next slide. All right, so this is my most bland slide. Historically, you know, reserves, I don't think it's news to anybody here. We're traditionally static values. When every, you know, BA I came to when, you know, originally started Duke Energy, these were all very deterministic numbers, very static numbers. Regulating reserves across the country, you know, also 10 was a popular, the number shall be this for all hours. Contingency reserves are still basically a static number. You know, even with a lot of solar and renewables, you know, and some codependencies there, that might move. There's talk of these moving to the contingency reserves moving to dynamic numbers, balancing reserves, operating reserves, especially regulating reserves. Historically static, starting to become, you know, more dynamic. So I don't know if the chart does it justice, but, you know, as I said on the previous slide or on the other slide, not all hours are created the same. So we have some hours of extreme ramping. The slide's a few years old, and we're starting to see ramps even more significant than this, dipping into nuclear. And then as solar goes away in the evening, we have our evening peak. Where, you know, our ramps are picking up as well. We certainly need a lot of, you know, down reserves as loads going down, a lot of up reserves as loads going up, and not a lot on the opposite side. And that's from a ramping perspective. Also from a forecast error, not all hours are created the same. I always like this chart. It's temperature versus load. I believe this is the Midwest region. But what I like about it, the size of the bubbles or the balls is the forecast error. And, you know, when it's 65 degrees, 70 degrees, you know, not a lot of forecast error. Load can come in, or temperatures can come in 5 degrees warmer, cooler. It doesn't really affect much. But as you start to get, you know, higher temperatures, you know, upper 90s, and maybe a shower moves in and crushes load, or the shower doesn't show up and load, you know, screams when it's really humid out, and we have a lot of air conditioning load. So definitely on the tail events, not only is load higher, but your forecast errors tend to be greater in loads in areas with high, you know, HVAC loads. And then taking all of those into account, you know, you don't want to solve for maybe, especially at the 5-10 minute scale. You know, you're probably not solving for every solution, but which tail events, you know, on the low side, on the high side, are you picking up for? You know, I'm not going to get into great detail there, but certainly, you know, how do you model these hours that are different and days that are different in season, all the seasonalities. So one of the places we started, EPRI published a few years ago, their Dynador tool. Originally, it was pretty much based in operations and real-time reserve calculations. They've added some functionality. A couple of us asked at the beginning, for some functionality for long-term studies. You can study all kinds of different balancing areas. Basically, at a high level, they've got whole presentations on this, but at a high level, you import your historical load, solar, and wind profiles. That's probably the hardest part of the tool, is trying to come up with, especially for future scenarios, what the load, solar, and 5, 10, whatever granularity you want, and then it calculates the stochastic forecast. What are we going to do with those? So a few years ago now, we entered into the DOE's OpSun project with the Department of Energy. EPRI is the lead. I'd be remiss to neglect our partners here, Duke Energy Southern Hawaii, and then UL, Virginia Tech, and Polaris. At a high level, there's 3 spokes of the wheel, or pillars of the project. First, you have to forecast, the probabilistic forecast. And when I was solar forecasting, we generated a probabilistic forecast. What do you do with it, right? So that's great. There's all kinds of data you can generate, but you need some method for managing that uncertainty. And it's great to standardize and simulate and figure out what those methods should be. And then the last pillar, and closing the loop, is to demonstrate it. They've got a scheduling management platform I'll share here in just a second. But it's to integrate those probabilistic forecasts. And then also there's some studies that go on the back end to kind of close the loop to evaluate which reserve methodology is the most optimal, least cost. So for the spokes of the wheel, there's lots of different ways to do this, and that's part of the DOE project. The traditional, I guess, where we started, you grab your percentile, 95th, 90th, 70th, 60th, whatever percentile, whatever it may be, in the up and down direction. You've got your, median forecast in the middle, maybe, 80th percentile on the top, 20th percentile on the bottom. And then another way to do it is to just generate a ton of scenarios. So you generate a lot of forecasts. That's, use number 2 on the right. And you run them all, and you minimize costs across all of the scenarios. So everybody, I think, at this point is familiar with stochastic forecast. Let's see, and then you calculate the reserves, and then you have to model them, right? And so what method do you use? And we've tested a few different methods here. I can't say this is exhaustive, and you don't have to really pick one. You could use one bounded by another. They've started with stochastic and running a bunch of different scenarios and generating the min cost. Next one's interval. How do you make sure you can get from one time step to the next for every timestamp, whether it's time step, 10 minute, 5 minute. One of the tough things is trying to figure out what that time step should be, whether 5, 10 hour, 2 hour, 4 hour, and every system's different, and every system kind of has its own constraints, day ahead, etc. Robust unit commitment. It's just taking the min max, right? So probably not the most efficient, but or optimal, but you're bounded. So that's another way to do it. We've kind of tested. And then dynamic reserves, or kind of that Dynador co-optimized dynamic reserves. Meet least cost. You can do that, and robust unit commitment. Really a research project. Not all of this is made into operations by any means, but evaluating what the long-term forecast is and long-term plan is for reserves. Let's see. So closing the loop is to demonstrate it. So EPRI's put a website out on their portal for Duke to use, and it's really has there's some animation on this slide if we were live, but you can toggle your prediction interval, your robustness interval, and you can do you want to do the extreme or prediction interval, and you can run all your different scenarios, and that's really probably the hardest part of stochastic reserves, and what we want to do here is what's useful to operations and what's useful on the end. I know ERCOT shared some of that earlier, but all of that is still I think an excellent area of research. And then closing the loop, there's the running unit commitment and economic dispatch on the back end. You run one forecast with one methodology, You compare it to another one, base case, change case, to evaluate the different, operations methodologies and to calculate what, if we ran it this way or that way, what would the, what were the cost implications of running different reserve methodologies. And this one is going to be, released as an open source project at the end. So to close it out, I have more questions than answers here, just like anybody else. What are the products needed? Do we, regulating reserves? We had the fast reserves in Ireland. We're not there yet in the Carolinas, but are we going to need those eventually? Contingency reserves, balancing reserves, etc. How do we integrate these across operations and planning? One of the, at what time scale? And this really varies by region and assets. And and some regions are not day ahead constrained at all. They have everything can start up in 4 hours, and they have plenty of gas, and there's no constraint there at all. Some regions are coal heavy and have a lot of day ahead requirements. One of the things we're trying to evaluate in the study is do these hold at scale? So if 5%, 10%, 20%, Ireland's there, so it'd be interesting to talk to them. That they're a little bit ahead of us in that regard. But these same methodologies hold as you double, triple your renewable penetrations, and then do they hold at interconnection scale? So we have a lot of solar in North Carolina. As our neighbors build out, how does that does it still hold with when the whole entire interconnection does that? The eastern interconnection does that, and then probably the last one. Do we want to? So in the forecast we're doing in the studies here, we're using the future forecasts and the stochastic forecast in the future. You can model it versus the future forecast or the historical performance and load and do your regressions, kind of the Dynador backwards looking, or do you do forward looking? Does it make a difference? All of that fun stuff. And certainly plenty of challenges, as was mentioned in some of the chats, just agreeing on definitions and what do you mean there. Aidan, that's about all I had for today. I don't know if we got a few minutes for questions.
Thanks, Rhett. Appreciate it. And yeah, I'll ask the other panelists to come back on as well, maybe turn on videos so that we can kind of go through some of the questions that have been posed on slide. I see questions for all the panelists, so I'm just going to kind of go straight to those. If folks are able to vote up or down questions, we probably won't be able to get to all of them here today, but if you can vote up or down, then that can help us prioritize. So we'll go back maybe and start with Tassos first. Tassos, there's a question there around the status and plans for the National Solar Radiance and Forecasting Database. You might also just mention what that is for folks less familiar, and then any of the future plans.
Sure. So there are two things here, right? Is the National Solar Radiation Database, the NSRDB, and that's indeed coming out of NREL. It's hosted in NREL, and we have already implemented hosting out of the Amazon Web Services as well, and other cloud vendors will follow to support essentially massive transfer of data. That is purely historical data from the satellites, the GOES satellites. They started in '98, and recently they upgraded to a 2x2 kilometer resolution capability on the satellites, that is. The product that is coming out of NREL and NSRDB is always upscaled to 4x4, but there is capability to get the high resolution data as well through the services I mentioned. When it comes to forecasting, we don't have such a database out of NREL, but the Solar Forecast Arbiter doesn't store, but gives you access to forecasts from a number of models that are being run by various services and are public, right? I mean, definitely the NOAA forecasts, NAM, HARE, all these models, you can access them for pretty much a very large number of locations out of the solar forecast arbiter.
Thanks, Tassos. Nitika, coming to you next. There's kind of two questions I'm going to merge together. One about the naming the vendors. I'm not sure that's necessarily appropriate in the commercial sense. You may or may not want to do that, but there is also a question around how you track and quantify when you're switching from one of those vendors to the other. Has that shown benefit, being able to use those two vendors? So you might be able to speak to that at least, and maybe you can mention who the forecast vendors are. Nitika, if you're speaking, you're on mute.
Hello, can you hear me?
Yeah, can hear you now.
Fabulous. So we do quantify, we do keep a track of our forecast performance of the individual vendors, if that's the question.
It's more about when the operators switch from one to another, have you tracked the improvement that you can see when you do that? I don't know if you're having audio challenges there, Nitika.
I am back if you all can hear me. Sorry, just having a variety of audio issues right now. All I was saying is, tell me if you can still hear me before
I can hear you, yeah.
Fabulous. So we do monitor our forecast performances on both the vendors. To be honest, one of the practice that we are trying to do or inculcate into our control room is not to chase forecasts per se. So we typically have one default selection that is based off of historic performance, and that is what we continue to operate on. And on days where there are concerns because fronts are blowing through and the selected forecast doesn't look reasonable, those would be the times when we'll really look to work on adjusting the selections.
Okay, thanks if you get that. Maybe Rhett, Damian, Tassos, I don't know if you have any thoughts on that around how you use different forecasts and whether that's something you've looked into.
If I can speak,
yeah.
If I can speak about Ireland, yes, I think the experience would be that there are two vendors used, and perhaps one vendor is better for certain conditions over other conditions, and that, yes, that would definitely be monitored. And I think also, as was mentioned previously, there are incentives given to the vendors to improve their forecasts. So there is a feedback mechanism to actually tell them, you know, this is what the real values were, this is what your forecast was, the other vendor is doing better, there are opportunities to improve.
Thanks, Damian. Rhett or Tassos, any thoughts on the kind of multiple vendor? You're on mute, Rhett, if you're speaking.
Yeah, there's not only, you know, different vendors, but different modeling approaches. You know, and different models work better for different tail events or cold weather events or you know, especially, you know, summer heat events. So yeah, not only different vendors, but even some of the vendors will switch between models for different, you know, conditions, especially with the HVAC loads we have in the Carolinas or even Florida. So
Thanks.
Well, if I have anything to add, you know, that's from what I hear from others on this front, and I have seen a number of entities going with multiple vendors when it comes to forecasting. It provides them, in their experience, better performance, right? Because some models will be better in certain times and, you know, not in others. I also presume there's an extra redundancy there for reliability purposes. So obviously there's, you know, some benefit all around. The question is, you know, is it what's the optimal number, right? I mean, is 2 enough? Do you need to go beyond 2? I mean, that's, I think, up for discussion.
It's nice to have three, even if the third's a simple model, because for when the two don't align, it's nice to have something to check. So, my experience.
That's a good point.
I think EnergyNet have three. I think they have 2 external and 1 internal. And then they blend them together in some clever way.
Yeah, that definitely seems like there's a move towards multiple vendors. Damien, the next question is for you around the SNSP and what's been done to raise it. I think you covered some of the topics, but if there's any specific things that you think are important for getting to that 95%.
A nice, easy question. I suppose SNSP, people tend to think of it in terms of stability, but actually, in order to get to those sort of SNSP levels, it also means that you need to have sorted out your steady state reactive power issues, your fault level issues, and all sorts of other things. So the challenge is that to get each level higher in SNSP, new problems appear that you need to resolve, which means that you need to implement multiple solutions. So to some extent, that is having a stronger network. So one of the weaknesses at the moment is that essentially there's only really one strong link between Northern Ireland and the Republic of Ireland. So strengthening that link means that the possibility of a system split disappears. It also means that you can relax the number of generators that you have online in the system. I talked about system services. At the moment, most of those system services are not really used in anger. So they are sort of future-proof measures for the system that will become more useful over the next decade. And I mean, a couple of them only really come into play whenever the system gets to 75% SNSP. So they haven't actually been tendered as yet. So it's a multiple number of different things, and they all need to come together. And I suppose the other one as well is increased interconnection. So interconnection with France as well, in terms of supporting the lower part of Ireland, also is important.
Okay. Thanks, Damien. Rhett, another one for you around you kind of alluded to this in your conclusions, but the faster than 10-minute regulating reserves, are we going to start needing to see more of those faster reserve products, maybe like what was shown in Ireland?
Yeah. I don't have any empirical evidence there for anything. It tends to be, as renewables increase, we've seen in Ireland and some regions with higher penetrations what we have in the Eastern Interconnection. Eastern Interconnection is one of the more stable places in the world. It's going to probably come here latter. I think we're leaning on Ireland to figure this out first.
Thanks.
Let us know. And I'd be curious when Ireland, what penetration they got there. I know they said it was added. What penetration levels to start to look out for it.
Damien, any thoughts on that as to when things, and actually maybe even Nitika as well, you're starting to see stuff in ERCOT. One of the questions here, one of the next questions is around kind of as well as forecasting output, will we also need to be looking at forecasting kind of grid services needs? Is that going to have to be considered more when we think about forecasting? Damien, Nitika, others, a few thoughts on that?
I can attempt to answer that. One thing that we have done is to look at the forecastability of things such as a fast frequency response service, and there's two nice things that come into play here. Is that you need more of these services whenever it's windy, so there is a natural correlation. So you need more whenever it's windy, and it's more available when it's windy, and also that it tends to be that the service that you get is less sensitive to variations in wind speed as well. So there's much less uncertainty regarding the volume of services that you might get. So I think the news is generally positive, but as you say, you do need to put the systems in place to actually forecast what you want and to ensure that you have it available to you. And the other thing that comes into play here is very much your SCADA systems and your real-time monitoring systems, so that you know exactly the state of play of your system.
That's a good point. Nitika, at ERCOT, is that something that you've been looking at as well with some of these kind of grid services that are starting to get needed? Is that something you need to forecast?
Certainly, as our wind and solar fleet is growing, certainly monitoring the sufficiency or the need for new grid services to maintain reliability is on our minds. We do have some ancillary service changes that we have market rules approved for that are pending implementation. Some of these are around fast frequency response, which is targeting a type of resource that can provide response within 15 cycles to help us with events really specifically during low industrial conditions. We've got a 10-minute capacity product, which is designed to help us with our ramp needs, net load ramp needs, as more and more of our solar growing. There is certainly a concern that we will also see a pinch on our ramping capability. But other than that, we are looking to do broader studies to assess what other changes we need to be keeping our line of sight on as our grid evolves.
Okay. We maybe time for one more question. The other one that I see that's kind of a general question here around EMS and implementing stochastic forecasts, which are changing how these are done. Nitika, you kind of mentioned what you all are doing in terms of the web-based service. Could you speak a little bit towards, how we might need to start changing how the EMS considers some of these issues? And maybe, I don't know if Rhett or Damian or Tassos have thoughts as well, but maybe Nitika, start with you. You're on mute.
I'm here. I mean, so we did talk with our EMS vendors when we were contemplating these system changes, and I mean, if some of this can be natively supported in terms of natively supported within the objective of the EMS, that's absolutely something we would support. At least in our case, it just felt like we had a lot of our entire architecture around consuming forecasts that our vendor generate is very specific to us, and coming up with this web-based platform outside of the EMS was to us a more, at least today, was more effective in giving us what we wanted for the control room and allowing us to maintain the reliability in our EMS. So that's why we started where we did, but I mean, absolutely will support EMS vendors natively picking up some of these capabilities.
I don't know if Rhett or Damian or Tassos have any additional thoughts on that question.
I have to say something here that our vision was that at some point the forecasting inputs will be fully integrated in the EMS, and we want to help the community to achieve that, at the easiest way and the fastest way possible, right? So that's one of the reasons that we have these discussions around commercialization in our workshops, to understand how the government can help the vendors, the end users, the research community build those products better and faster, right? So we have some ideas. I'm not yet at liberty to talk about, but stay tuned.
I mean, that might be a good place to kind of wrap it up. So I would like to thank all the panelists for their great contributions and discussion today, and thank everyone for participation. It's a good, timely, and interesting look at some of the practical aspects associated with forecasting and operations, which is where the rubber really meets the road. So as a reminder, we'll follow up with the written answers to the questions we didn't get to during the Q&A. I also want to just remind you we're nearing the end of the Meteorology and Markets workshop series, and the last session isn't scheduled for next Tuesday, so that'll be a closing plenary, and it'll be chaired by my colleague Eric of EPRI, who's the co-chair of the working group, and me here at ESIG as well. We'll be closing the loop on the opening plenary session. We'll look at the energy adequacy and market design aspects of the Texas events from February. No charge for the sessions as usual, and you're all invited to attend. Further information is provided on the ESIG website at esig.energy. So thanks again to the panelists and participants. Thanks again to ESIG, and stay safe, and we look forward to seeing you again on Tuesday. Thanks, everyone.